One of the more practical applications of vector concepts is in the study of physics. Students often lose sight of the fact that Newton invented calculus in the process of trying to understand physical motion. So we will be taking a short tangent into physics to see how these ideas can be applied. Specifically, we're going to explore the concept of work. There are two vector quantities that are relevant to this topic: displacement and force. Remember that displacement is the relative motion of an object. When we were adding vectors, we thought of the sum of vectors as indicating one movement followed by another movement. Those movements are displacements. Notice that they have both a magnitude and a direction. The idea of a force is a push or pull applied to an object. When you bring magnets together, they generate a force that either tries to pull them together or push them apart depending on the polarity. Gravity is a force that pulls objects together. Notice that forces are also vector quantities because there's a magnitude and a direction. As you bring magnets together, the direction of the force on each magnet is either towards or away from each other, and the force gets larger as they get closer together. It should hopefully make intuitive sense that applying a force to an object can lead to its displacement. Work is a measure of the energy used when applying a force to displace an object. As we are applying the force to the object, we are causing the object to move, and the work is the conversion of the applied force to the kinetic energy of the object. There's obviously a whole lot more we can say about this, but that's the extent of the intuition that we're going to develop for this course because we were going to consider only very basic cases. The formula for work turns out to be a dot product. Work is force dot displacement. Once again, notice the vector symbols over F and D, but not W. Work is a scalar quantity. The reason for the dot product is related to the fact that only the part of the force in the direction of motion counts as far as energy transfer is concerned. If we are pushing a cart along a track, we do a better job of putting energy into the cart if we push parallel to the track instead of at an angle. The more the force aligns with the motion, the more energy is transferred. When solving one of these work problems, you will want to draw a picture to help identify the force and the displacement. From there, just take the dot product of the vectors. Depending on the problem, you will either use the geometric formula or the component-wise algebraic formula. A common error that students make is that they do not put the tails of the vectors together when they calculate the angle. The activity for this section provides a little bit more insight into the concept of work, so you should definitely take the time to think about that one. Let's take another look at pushing the block around the track, but pushing at an angle. If we think about it, the only part of our force that is doing any work is the part that's parallel to the track. There's another part of our force that is perpendicular to the track, and it's doing nothing useful at all. And this hints at the usefulness of breaking a vector down into two separate pieces that reflect the underlying problem, where those two pieces are either parallel or perpendicular to a specific direction. In this problem, we're looking at the direction of motion, but this can apply to any direction that's relevant to the problem. The projection of the vector u onto v is the part of u that points in the direction of v. Here's a diagram that indicates how the projection is determined, and we'll look at the details of this briefly. The notation is slightly cumbersome, but it is a fairly common notation. Notice that the vector we project onto is a small subscript to the PROJ. We've put a vector arrow over this because it's a vector. Very few books do that, and it honestly looks kind of ugly. But I think the emphasis is more important than the aesthetics. For the part that is perpendicular, we use this notation. You might remember this symbol from a geometry class, and it represents perpendicularity. So this is the projection of u onto the direction perpendicular to v. And this quantity is also a vector, so it also has a vector arrow. The geometry of a projection can sometimes be difficult for students to visualize and draw. So we're going to describe it in a very prescriptive way that helps to avoid errors and do a couple examples. When drawing the vector projection of u onto v, first draw the two vectors with their tails together. If you can, draw v a little bit lightly so that it doesn't become a distraction later. Then extend the vector v into a line. Draw a line from the tip of u to the line you just drew so that the two parts are perpendicular to each other. The projection of u onto v is the vector that points from the tails to the point of intersection. Here are some pairs of vectors u and v. You should pause the video and see if you can visualize how to construct the projection of u onto v for each pair. In each of these cases, you're starting off with step 1 already done for you. Extend the vector v into a line, find the correct perpendicular, and use the intersection point to create the projection. Here are the results. Notice that in some cases the projection vector points in the opposite direction of v. Also notice that one pair has the labels u and v swapped, and they give different results. This emphasizes the importance of knowing which vector you're projecting onto which. The reason I teach students to draw the line through v is because some students turn their pictures into triangles by connecting the tip of u to the tip of v, and that leads to problems. It also deals with the case when u and v point in opposite directions, which is also a source of confusion. By drawing the extension explicitly, I have found that students make those errors much less often. The derivation of the formula is in the book, and you're encouraged to work through that yourself. It's just a quick exercise in applying the properties of the dot product. There's another way of writing this vector that provides a little more insight. Notice that in this second form, we have written it as a product of a scalar and a unit vector in the direction of v. The scalar is called the component of u in the direction of v. Notice that if the component is negative, then the projection points in the opposite direction of v. Lastly, we can get the perpendicular projection by manipulating the definition and making a substitution. I find it's much easier to think of this relationship in solving for the perpendicular projection rather than memorizing the final formula. As a general rule, I recommend against memorizing formulas because they often do not increase your level of understanding, and you won't know that you don't understand until several sections down the line, and at that point, you're stuck trying to play catch-up. Vector projections are important for multivariable calculus, so it is important that you are conceptually and computationally fluid with them. Make sure you take the time to do the exercises in the book to make sure that you're where you need to be with this topic.